I didn't hear it. Aganusha Akorja. My name is Paul Cunningham. Welcome back to the last session on the final and fifth day of IST-Africa 2022. We're going to have presentations from the Czech Republic, South Africa, and Kenya. And our first presenter, Karel, I'd like to thank him for being flexible enough to allow James to swap sessions this morning. So Karel's presentation is on an optimization of African LULC database for sustainable development.
Hello, my name is Dmitry Kozhov, and today I would like to present for you optimization of African land use land cover database for sustainable development, namely Open Land Use for Africa, and there is work done and with my colleagues that are coming from many different countries. So now I will tell more details about it. So our objective is to present and demonstrate open land use database for Africa and its development, and basically our work is aimed at building seamless harmonized vector land use and land cover database for the whole of Africa in order to foster open access and utilization of generated vector layers via a web platform for anyone who is in need of such data, who is in need of doing some analysis and evaluation of land use and land cover. So we are grounded at a database model which is quite advanced, and it is flexibly able to flexibly incorporate different thematic attributes from different domain. It is able to define structure of reference geometries and also their hierarchy. So, for example, for one type of applications, we would need more detailed, and for another applications, less detailed reference geometries, and we could provide those to our clients. And also the thematic attributes is flexible. It's possible to add thematic attributes from one data source from another data source, depending on the wishes of clients. So we want, for example, to have soil attributes for one client linked to our reference geometries. We are able to do so. For another client, we're able to add climatic data and link them to our reference geometries, and this is all done hierarchically. So we are working with different scales and different applications without problems, and we are linking all this semantic data to all objects, as I was speaking. To export data, we're using concept of spatial temporal semantic views, and we tailor them by the wishes of our clients. So in Europe, our database is comprised of publicly available data sources coming from European Environmental Agency, for example, Copernicus program, ESA, and national governments, for example, land parcel identification system, cadastral data, urban atlas, Korean land cover, and also for custom applications, we're using observation data to get some specific insights that are needed by clients. And for Africa, we integrate territorial units that so far that are coming from OpenStreetMap, and for semantic layers we use a combination of different sources that I will speak about in a second. So the work is derived in some steps. At first, we are building the basic geometry, and among different versions of open land use, it was a priority to use one on another data set. Currently, I will speak about what is used currently in the next slides, and then also to get some insights by using the unsupervised classification of Sentinel-1 and Sentinel-2 imagery, and we integrate those with thematic data and with our basic geometries. The first version, it was done of open land use, it was done in 2018. Then in 2021 it came the second version, and currently the work is done on the third version. Here how it looked like in 2018. Just every cover dataset was available. It had a 30 meters resolution, and it was quite outdated. For example, here we look at the border between Kenya and Uganda, concrete at Busia city, and so how this is how they looked land cover around it in the year in 2018, with the first version of all of Africa came. Then the second version, it was the geometries were based on OpenStreetMap, and you already see that it's much more detailed, and a schematic data source that was combined with this reference geometries to define land cover. We use Climate Change Initiative land cover dataset, which was derived from Sentinel-2 imagery. The data was coming from year 2016, and you can see already that it's more detailed than this AfriCover dataset. You can see the structure of the city of Busia, how it goes along the road, and also it's possible to identify some forests that grow along some linear features, I think rivers. And then this data, it was combined with this reference geometries derived from OpenStreetMap, and here you can see the resultant data set. We thought that it is quite a good result comparison to the first version, so we extended it to cover the whole Africa. It's not possible to show in one slide how it looks for the whole Africa, because those are millions of features. It's impossible to render on this size. So here it's just an example of how it looks in surroundings of Victoria Lake. And now we are working on the third version, which will also incorporate the data from ESA World Cover dataset. It's 10-meter resolution dataset from year 2021 that ESA publishes, and it contains detailed information about land cover, and also it's quite good idea to even because OpenStreetMap doesn't cover Africa equally good in all areas, so it's a good idea to vectorize it and to use it also for the building of reference geometries. So this is what we done. For example, here you can see the combination of the geometries from OpenStreetMap as a world cover that constitute basic geometries, and the thematic information is taken from as a world cover data set again. So if we zoom in, we can see that it's more detailed. You can see already some objects within the city that is not built up area, and you can see very clean the structure of the city and how it goes. And also, I think we think that this idea to use Sentinel-1 and 2 imagery and their unsupervised classification is very useful. So here you can see that you can get even more detailed view on the land cover in the city if you overimpose this data from unsupervised classification. So here you can see that you can see more clearly the density of the build-up areas around the city, and also some objects of different land cover within the city. Here also there are some insights that could be derived from the composition of unsupervised classes within different OLU objects. Those information can be evaluated for different thematic application or for different customer needs differently. So the benefits of our database is that it's published as open database, everyone will access to it. Also, it covers the whole Africa seamlessly. It incorporates different semantic sources, and it can be obviously extended by the customer needs depending on their needs and their applications that are developing. And also, there is no any other data sets that does something as we do. We are generating, now we will generate the whole Africa based on the approach with as a world cover data, as I was speaking about, and we will help different applications to provide this data for their analysis. So I thank you very much for your attention, and I hope for your support.
Karel, can you share a little bit more insight into the links that you provided in the chat?
Okay, yes, I can try to explain. As the most of these activities is running as part of so-called Inspire Hackathon. You can remember that in Kenya, when was the last in situ, yes, we organized this hackathon directly in Nairobi, and we continue with this group. Yes, this group was formed about the activity which we called Smart AfriHubs, and now one from the goals is to make this map across all Africa and be able to integrate it also other data. And we are now also preparing working on the new version of portal. We had in last 2 weeks 2 training with some people from Africa how to use and how to be possible to publish the data, because we would like to build some social space where it will be possible to making data for Africa easy available as open data. And we will be happy to cooperate with any organization, any people, to discuss how we can integrate it, how we can work. I will put to the chat my email, so if anybody will be interested to contact me, yes, come to me, and we can discuss how we can cooperate, because we would like to extend the services. Now there are some people from Nigeria, from Kenya, from Burundi, working long time inside of our community. Also for people who will be interested to cooperate, please contact me. And because most of people in Africa prefer this type of the communication, we have also the group on WhatsApp, which is exchanging information about the event, about the development, and trying to help with the data and help with some improvement of agriculture, environment, and other things in Africa. So anybody who will be interested is welcome to join this our effort.
Thanks, Karel. So what are some of the challenges of integrating so many different potential data sets, and what are the opportunities for the future?
Yeah. I think that we are looking what is available. Yes, on AfriHub we integrated different data coming from different sources, from FAO, from other organizations, and we are trying to make easy work with this data. Just a moment, I will try to share with you some information from YouTube, where we make some lecture how it's possible to use this new technology. Again, you can see these videos, and you can eventually ask for some other explanation or cooperation. This platform are fully, after registration, fully open. We support, for example, the connection of this platform with QGIS as open source, because we would like to fully support usage of open sources, because this could be some way, and in some way we see this this activity mainly as some capacity building and also the training and cooperation.
That's great, thank you. So does anybody else have any questions or comments?
Yes, I put links to YouTube where you can see this training which we done with the people from Africa about the possibility to publishing data, because on this platform anybody after registration can publish its own mapping data.
Got you. Thank you very much indeed, Karel. That was very interesting. So our next presentation is on intelligent and flood resilient agriculture.
Good morning, good afternoon. The title of the presentation being given is Intelligent and Flood Resilient Agriculture. The research was conducted by Ayodele Periola, from the Department of Electrical and Electronic Engineering Technology at the University of Johannesburg. The name of the presenter is Ayodele Periola from the University of Johannesburg in South Africa. The challenge being addressed, problem being studied, is on the influence of flooding in crop production. So crop production suffers devastating effects from the occurrence of flooding. Recently, there has been flooding observed to have occurred in KwaZulu-Natal, which has led to destruction of crops and farm fields. This has received significant coverage by the media, in the press, and this the picture has been shown here, showing the effects of the flooding at KZN, showing destruction of farmland and roads. Floods also destroy jobs because they destroy urban farming activities and initiatives. The case being seen here, which left-hand side is the case of urban farming, where vegetables are grown in urban areas. We can focus on KZN, and then on the right-hand side, showing destruction, the post-flood case, how the environment was after a flood, and this impact on jobs, the impacts on the economy. In this case, the impact on the economy of KZN. KZN is being considered because a recent case of flooding has been observed in that region. So flooding also causes the destruction of crops that would have been exported, such as sugarcane. Sugarcane, in this case, it also destroys potential exports. It reduces the volume of exports for the country, causes food insecurity, leads to job loss. The objectives of the research is to propose and present a new solution. The new solution limits the impact of flood on agriculture. The second objective is evaluate how the new solution reduces crop loss. This is done via simulation and performance evaluation. The first aspect we present the architecture design of the proposed logical plant unit. So the logical plant unit basically is able to utilize locations, multiple locations to grow, to enable crop growth. In this case, it uses area location. It combines that with terrestrial locations. The use of the logical plant unit incorporates location diversity, in this case, physical location diversity, and the occurrence of flood. An area location, which is an altitude above the ground, is used to support the plant. Presents the case of non-terrestrial agriculture, land-led farming. So the architecture of the plant presented a logical plant unit is basically a plant equipped with aerial entities enabling it to occupy locations the given altitude of the ground. It's equipped with computing entities which are able to sense the increase in level of water, then store this data in data module by a computing payload. The data module is hosted by the aerial entity, which comprises of several micro drones. So the heavier the plant or the crop, the more micro drones are used to overcome the weight and be able to build the crop. And then the crop itself, the plant is a biological entity in the proposed research. The second aspect focuses on performance formulation and evaluation. In this case, there is the number of lost crops is formulated as a metric. Performance simulation is done to evaluate the number of lost crops. In this case, the performance simulation is done using MATLAB, and then the results from MATLAB are further evaluated to determine the benefit of using the logical plant unit. The results are presented for a case of a single farm and two farms, considering the existing approach where crops are basically grown on ground. The existing approach considers new farming paradigms, such as soilless farming, the conventional way of growing crops, the use of greenhouses. All of these approaches are terrestrial based and are prone to be destroyed in the event of a large flooding incident. So the case of our proposed approach is the case where the logical plant unit is used. In this case, plants can stay on the ground and can still maintain a location at a given altitude where they are above the ground level in the event of flood. The simulation also considers the case of a big farm. Each of the farms are very big, and some portions of the farm are affected by flooding, while some portions of the farm are not affected by flooding. This has been considered to make our simulations reflect more of the scenarios. It's not considered a case where there is a disastrous flood that affects an entire city. Simulation considers the case of partial flooding where some parts of the farm are affected, some other parts of the farm are not affected. This is the reason why the number of lost crops keep changing. The cumulative number of lost crops have not been investigated, but they can be easily derived from these results. This result shows the instantaneous number of lost crops, considering the asymmetricity and distribution of flooding on the farm. So, and different number of epochs have been considered in this case. The number of epochs vary from 2 to 18. An epoch simply represents a given point, a given observation of the farm during a flooding event. So more epochs mean we observe a portion of the farm for longer periods, or it involves looking at more portions of the farm. So the number of epochs is considered in two sets. The previous list shows number of lost crops for a case where we have 2 to 18 epochs, the existing scenario, and the proposed approach incorporating LPUs are used. The second set of results show when we have between and 32 epochs. The number of epochs have been separated in this case for purposes of clarity. An analysis of the presented MATLAB simulation results show that the use of LPUs as seen in the existing scheme reduces the number of lost crops. Further evaluation also shows that the number of lost crops is reduced by at least 10% and by up to 33% on average by using LPUs. These performance benefits are of course expected and will go up in the case of a disastrous flooding scenario where an entire farmland will have lost all the crops in the absence of LPUs compared to the case where LPUs are used. Thank you for your attention.
Thanks, Ayodele. Can you talk about some real-life examples of aerial and non-terrestrial agriculture? And if you could also discuss the associated challenges, opportunities, and learning curve for farmers. Thank you.
Thank you, sir. With regards to real-life examples, what I've been able to see from the literature is urban farming, examples of urban farming, greenhouse farming methods, hydroponic farming. That's what I've been able to find. The closest approach to aerial farming in literature is growing of crops on upland areas, which will otherwise not be useful. So with regards to the challenges with the algorithm is the solution is not suitable for all type of crops. If we are going to use it to grow tuber crops like cassava, like yam, then it becomes very challenging because then the transition between locations involve moving the actual fruits, the crop, the desirable crop from location between different locations. But the case envisaged there is for crops like maize. Is crop.
Yeah, sorry, Ayodele. I think towards the end, the sound was going away a little. So my understanding, just to clarify, is that upland agricultural areas are areas that traditionally would have been used for grazing rather than plant production because they may have unfortunate temperature, the weather may be bad, there may be a short crop season, the fertility of the soil may be poor, and there may be a lot of rain. Is that correct?
Yes, sir.
Perfect. Okay. Does anybody else have any questions or comments from Ayodele? In which case, thank you very much indeed for highlighting this important issue. Our next presentation is by Andrew, who's going to discuss water quality management using IoT and machine learning.
Invited guests, all protocols observed. Invited guests, my fellow presenters, ladies and gentlemen, I want to welcome each and every one of you to our presentation today in the area of water quality monitoring using IoT and machine learning. My name is Andrew Omambia from the University of Eastern Africa, Baraton, My co-presenters are Bernard Maake, Kisii University, and Anthony Wambua, Daystar University. Maybe a brief introduction of myself. I'm currently a tutorial fellow working at the University of Eastern Africa, Baraton, in the School of Business, Department of Information Systems and Computing. I did my undergraduate in the same university, that is Baraton University, in the area of Business Information Technology. Later on, joined this university doing a Masters of Science in Information Systems. I'm currently undertaking my PhD in Kisii University in the area of information systems. This topic is going to be discussed under the following subtitles: Introduction, Motivation, Research Objectives, Methodology, Results, and Conclusion. I want to echo the words of my professor during my undergraduate days, who kept on saying, water, water, water everywhere, and yet too little for drinking. These words never made sense then until we started undertaking this study. Safe water for human consumption is considered as essential for human life. You actually realize that it is essential for human consumption. That is according to Lucas et al. 2011. Without clean water, it would not be possible to sustain life on Earth. Of course, that is why probably there is some percentage of this world is made up of water, but it is very difficult to get water for drinking. Maybe because of a number of reasons. One of them is urbanization. You'll actually realize that urbanization led to industrial pollution. And of course, the World Bank report of 2018 reports that access to clean and drinking water is highly compromised. Of course, more than 2.5 billion people do not have access to clean water. This is according to the World Bank report of 2018. More than 4 billion water-related diseases really happen each year. Of course, around 3.4 million mortalities are usually associated with drinking and safe water. This is really a great concern, an issue that needs an urgent concern. Chlorination is actually the most common option for drinking water, especially in many of the cities. And of course, chlorination deemed harmful, especially in looking at the factors of behavioral and also with urban treatment and uncontrolled water quality parameters and many other factors. Water disinfection through chlorination has actually proven to be ineffective. And of course, that is according to the world, that is according to Farid et al. Chemical discharges can contaminate from the water treatment plants. Traditional water quality analysis methods. The wastage of water during distribution due to the damaged pipes and IoT can be employed to detect such occurrences in real time. This paper then presents a development in machine learning and IoT for detecting the suitability and the flow of drinking water. The study findings from this paper will actually be able to help waterborne diseases. This paper is guided under the following objectives. Review technologies used to detect and monitor water leakages and pilverages. Review technologies used to detect and monitor water quality. To determine an IoT model for monitoring water quality and leakages. To make recommendations for existing water quality and leakages monitoring system. This study actually proposes that this study proposes a system that uses several sensors. And of course, we shall be able to look at those sensors. Of course, the sensors are attached to the city backbone for fresh water supply. Having those sensors at, of course, strategic points could be able to if there are water leakages and fill varieties. And of course, the complete system overview is depicted in the figure below. You can be able to see we have four um, the sensors, sensor 1, sensor 2, sensor 3, and sensor 4, and of course, which are connected, directly connected to the controller, which means the controller will be able to access data from those sensors and, of course, send the same information to Raspberry Pi. In, uh, in turn, the Raspberry Pi will be able to send the information to data center, and of course, from which all the handheld devices will be able to fetch the information from data center from the cloud. Proposed system will actually have the following sensors. Of course, we have the temperature sensor, which will be able to monitor the temperature of water. We have stability sensor, which will be able to monitor stability sensor, which monitors the presence of suspended particles. Flow sensor, which monitors the flow velocity of water. Of course, dissolved oxygen sensor, which monitors the amount of oxygen present in water. pH sensor, which monitors the amount of acidity and alkalinity of water. Of course, there may be a need for specialized chemical sensor, which can be added to check specific chemical. These sensors will be distributed at different points, of course, of the water distribution backbone. And of course, this will be ideally measure and monitor water parameters that determine how safe and how quality is actually that water. Of course, there will also be other components like controller. Controller extracts data from different sensors and sends the same to Raspberry Pi. Raspberry Pi is a component that interfaces the controller and the data center. Of course, data center, this is a subsystem which is placed in the cloud that connects the Raspberry Pi to an IP address. Of course, we have the end user system. This module consists of different devices that end user will access information from the data center. This paper proposes a model that utilizes IoT and, of course, machine learning. And of course, we want to see that IoT and machine learning will have their distinct functionality. So several benefits can be accrued from the implementation of this proposal. This, of course, the benefits of this implementation of this system will be the following, but not limited to what we have there. Detect water pilverages and leakages in real time. That will be done actually in real time, because detecting the leakages and pilverages. Then the system will actually be able to monitor parameters such as alkalinity and acidity, dissolved oxygen, and stability of water for decision making. Once those parameters are detected in real time, then the best decision or informed decision will actually be made by the relevant stakeholders. The community will benefit from high quality water, drinking water. That will be ensured by actual implementation of this system. Researchers will also benefit by having a model that can easily be converted into a working product. This paper also explores the potential of machine learning and IoT to explore water challenges in cities. Of course, here in this system, IoT will provide a heterogeneous network of devices. And of course, machine learning will make such devices smart. So the system will avail such crucial information to the relevant end users. Of course, the others will develop a prototype of the proposed system, and that prototype will be very useful in the following ways. One, to determine appropriate interconnection technology for devices in the Kenyan context. To also be able to determine the accuracy levels of different classifications algorithm and also determine the accuracy of message auto-generated by the systems and sent to the different users. Thank you very much. That is the end of my presentation.
Thanks, Andrew. Obviously, water management is highly regulated and controlled in many countries due to its strategic importance. So what engagement has there been to date with local municipalities to investigate a willingness to evaluate the proposed sensor solution and assess and validate the potential cost-benefit analysis of using IoT and machine learning in the field to monitor water quality management? Thanks.
Thank you. Thank you very much, Mr. Chair, for that really very informative question and really an eye-opener. I really want to agree with you that the water sector is highly regulated sector across the globe and especially here in Africa. Actually, the situation in Kenya is even worse because many times you actually realize that the regulation and especially the policies in municipalities really have a lot of gaps. But I want to say that that being said, I have realized that many times, especially in Kenya, we all agree that there is a problem that is really very core. And now the authorities have actually started now engaging actually what we call multi-sectoral collaboration or multidisciplinary actually collaboration, where people from various aspects come together to really discuss about this challenge. And that is why we are coming in from the IT perspective. Of course, there are those from other areas like chemistry and areas like that. That's why we are coming and saying, yes, here there is a problem, especially in areas like slum areas like in Nairobi, where you'll actually find that much of the water is contaminated because of the leakages. And many of these actually authorities are now agreeing that let's come and probably come up from the policy and see how we can be able to help this. In the aspect of cost-benefit analysis, actually, you'll realize I said somewhere in my presentation that most of those sensors are actually manageable in a way. And of course, you'll actually realize that they're not really very costly. For now, because it is an ongoing work, we are going to further engage in research to really understand how we can even collaborate, even as like IBM and things like companies like that, really see if we can be able to send large quantities, then the cost can even go down further. Thank you very much, Mr.
Thank you very much, Andrew. Are there any other questions or comments? In which case, we're moving on then to our final presentation of the day and the conference. So no pressure here. Application of convolution neural networks to the quantification of tick burdens on cattle using infrared thermographic imaging.
Hello everyone, and many thanks to the IST-Africa for the opportunity to present this work today. My name is Mudau, and I'm a postgrad student at Stellenbosch University in the Faculty of Agri-Sciences in the Department of Animal Sciences in South Africa. I'll be presenting some of my research findings on application of convolutional neural networks in the quantification of tick burdens on cattle using infrared thermographic imaging technology. This study was motivated by difficulty in selection of tick-resistant animals for breeding when using tick counts. Ticks are hematophagous ectoparasites of livestock and imported vectors of diseases, which cause significant losses in sub and tropical livestock production. For the past 100 years, acaricides have been regularly used to control ticks and tick-borne diseases, and they are currently regarded as the most effective chemical tick control method. However, studies have shown that ticks are developing resistance against chemical acaricides, which has led to development of new drugs, further increasing the production costs. It is essential to understand the level of tick infestation in animals in order to implement an effective chemical tick control method. As a solution, tick-resistant animals can also be used as an alternative tick control method. Nonetheless, in cattle production, difficulty in selection of tick-resistant animals for breeding using manual tick counts is rapidly becoming a problem, as I've stated earlier. The manual tick counting method that is currently used is based on counting ingoid female ticks sized between 4 and 8 mm in length by palpation on one side of the animal and then extrapolating to the whole body by multiplying by 2. This method has several shortcomings. For example, the process is slow and tiresome, and it is subject to psychophysical and visual phenomena. In addition, the animals often have to be restrained, which negatively influences the welfare of the animal. Cortivo et al. Used thermographic images combined with a program for automatic counting of ticks. However, this method was found to be not completely automatic, since tick counting must still be done manually. Hence, there's a need to further evaluate the algorithm for automated tick counting. The main objective of this study was to train the convolutional-based algorithms for detection and quantification of tick burdens on cattle. The data was collected in the following way. For image capturing, a Flare 1 camera was used to take pictures of ticks on cattle. Then, after manual tick counting, a certain area with known number of ticks was delimited as the region of interest using a square wire for capturing thermal images. If you can take a closer look at this picture right here, you can see a hand holding a square wire. So this square wire was used to delimit the area with known number of tick counts. And then the camera parameters were adjusted, taking every 10 minutes to account for temperature variations, and emissivity was adjusted according to the manufacturer's recommendation. So it was adjusted to 0.98. All images were taken from different angles. As you can see here on these pictures, they were taken from different angles and at different distance, and at a distance of plus minus 1 meter from the animal. The photo session took place between 9 a.m. and 4 p.m. Then for image processing, everything outside the region of interest was then cropped out from the rest of the images. So we took these thermal images, cropped out everything and then we're only left with the region of interest. So these are the images, these are the cropped images from the taken thermal images. So these processed thermal images were then classified into two categories, which was the more than category. So the more than category consisted of those images with more than 5 ticks, and then the less than category consisted of only those thermal images with less than 5 ticks. If you can take a closer look at these images right here, there are less than 5 or equal to 5 ticks only, whereas the other ones display those images with more than 5 ticks. Then all images were normalized to the same size before importing into the architecture. And to train a neural network to detect ticks, the CNN was implemented in Google Colab, where deep learning algorithms for image classification were trained using two deep learning architectures, which was ConvNet and MobileNet. So these architectures were trained for rapid and accurate tick quantification. The train set and validation consisted of 852 and 272 images respectively. Artificial sample diversity was used to prove the performance of the algorithm by enlarging the original dataset through data augmentation and optimizing the deep learning model by several major parameters such as normal size of images and deep learning network architectures. The algorithms were evaluated and validated for rapid and accurate tick detection on two different infestation levels. Those infestation levels being the less than 5 and greater than 5. The validation data was used to evaluate and validate the performance of models. The architectures of the convolutional neural network includes convolution layer and hidden layers. In this study, firstly, a data pool was created by collecting 1,124 tick thermal images. These are all images that were taken or that were captured from the cattle. And the next step was to develop deep learning models. After developing the deep learning models, they were introduced into the architectures, which then produced the tick counts, or which then were able to predict the tick counts. So now this is our convolutional neural network. And if you can take a closer look at the input, it consisted of the images or thermal images from the data pool. Our CNN architectures make the explicit assumptions that the inputs are images, which allows for encoding of certain properties into the architecture. These then make the forward function more efficient to implement and vastly reduce the number of parameters in the network. Each hidden layer is made up of a set of neurons, where each neuron is fully connected to all neurons in the previous layer, and where neurons in a single layer function completely independently and do not share any connections. Then the last connected layer is called the output layer, and in classification settings it represents the class scores. When applying the convolutional architecture into our algorithm, the training was done on all 852 train images for 15 epochs, and validation was performed on all 272 validation images. During training, the network was commanded to discover what kind of features the convolution had learned from the dataset. The transformation of images during training was observed. Training our network over 15 epochs takes approximately 20 minutes. Early stopping was employed, and the model from the best performing epoch on training data was used. These figures show the training validation accuracy and loss collected during training. The training accuracy approached 90%. The training accuracy in this second chart it's shown by the blue line, so it reaches its 90%, whereas the validation accuracy stalls at 60%. The training loss reached its minimum after only 15 epochs. However, if I may bring your attention to this first chart, you can see that there's a lot of overfitting displayed here by the validation loss, and this could be result of the relatively small number of images that were fed into the architecture. Well, for our mobile net architecture, these are the learning curves of the training and validation accuracy and loss when using the mobile net v2 base as a fixed feature extractor. After fine-tuning, fine-tuning is represented by this green line here. So everything that you see after this green line is what happened after fine-tuning. After fine-tuning, the learning rate was decreased to adapt the pre-trained weights, and the validation loss is much higher than the training loss, which indicates the chances of overfitting. Overfitting in this case could result as the new training set is relatively small and similar to the original MobileNet v2 datasets. After fine-tuning, the model nearly reaches 98% accuracy on the validation set, and the performance of the model was evaluated on new data using a train set. After evaluation, the model was then ready to predict whether a certain was then ready to predict whether a certain set of images falls under the less than category or the more than category. The model was used to predict whether the images fed into the network belong to the less than or more than category and had achieved an accuracy of 100%. So if we can look at the images that are labeled less than, you will definitely see that they are less than 5 ticks, and at those that are labeled more than, there are more than 5 ticks there in the thermal images. In conclusion, the CNN architectures can be used to develop smartphone applications for detection and quantification of ticks. Then the use of infrared thermographic imaging technology and machine learning in tick enumeration has a great value as it eliminates the time-consuming and often inaccurate manual tick counting approach. An algorithm for a cheap, rapid, and accurate method of phenotyping animals that was successfully trained will assist farmers with the optimal application of acaricides to control ticks and tick-borne diseases. Furthermore, it facilitates selection of breeding heads for tick resistance. This method will save farmers money by reducing losses associated with ticks and tick-borne diseases. The images used for training the algorithm to detect ticks in this study had poor quality due to the camera specifications. Hence, it is recommended to use camera with better resolution and sensitivity and capturing images aiming at maximizing the contrast between ticks and the host animal to obtain high accuracies when training the algorithm. Future studies should also include larger number of different breeds under different local environmental conditions for better results. Additionally, further studies should use this technique to develop other technologies for simultaneous tick quantification and identification on cattle. Thank you for your time and listening. I would like to extend my gratitude to the following partner institutions and collaborators.
Thank you very much for a very interesting presentation. And I love the sheep at the end. So one of the issues that I'd like you to briefly discuss is what are the implications of accuracy with different types of cattle? Because their skin may be different, the colors may be different, and I'm just curious as to what the implications of that might be for the thermal imaging. And then what are the potential implications of taking the images between the timeframes that you mentioned? And how did you validate the accuracy of the results of the analysis of the cropped thermal images? And then finally, what about the ticks outside the size range that you mentioned earlier in your presentation? Thank you.
Thank you for the question. As to regard the different cattle breeds, I used different cattle breeds and I took thermal images from different cattle breeds. And then since they all have different skin or the coat, so I was able to train the algorithm to detect ticks and also to identify the difference between the ticks and the coat skin. Hence, I used the thermal images. So I was focusing on the temperature, that is the temperature and radiations that the thermal camera was capturing from the ticks and the animal. So it was able to differentiate between the skin of the animal as well as the skin of the ticks. As also, I also used the size of the ticks as well as a parameter of detection. So the algorithm was then able to also not only look at the temperatures, but also at the size of the objects that it sees on the picture. And also, so the temperature that is recorded from the ticks, as well as the size of the ticks, was major parameters that I looked at. And what was another question?
Yeah, so the other question relates to ticks being outside the size range, because presumably, like other creatures like mosquitoes, as the tick consumes blood, it gets bigger. So I'm just wondering how you deal with ticks that are outside the size range that you mentioned.
Okay, so I did not only focus on one size of the ticks. So I was able to capture the ticks from the nymph stage up until to the fully engorged ones. And it was not only one tick species. So we had about 5 tick species, which has different sizes. And then that's what built the accuracy of the algorithm, because it was able to identify the ticks that are of different species, not only one species, and it was both males and females. Because if we are using conventional methods of identifying ticks, we only focus on looking at the female ticks, but on this one, I was focusing on both females and males, as well as the nymphs as well.
I understand. And my understanding is that it's primarily the females that suck blood, or am I wrong about that?
No, you are right. There is the females that engorge. So for some species, it's impossible to see the males, because they when the female engorge, then you can't see the males. They're underneath the females.
Got you. I understand. Right.
Like Buflas, Decolaratus, and Microplas.
Okay, and then the other question I had was, are there any existing tick image related data sets available that you're aware of that you could use to supplement your manually created training data? And how could such data be shared across the continent? Because presumably there's a variety of different types of ticks, and the infestations in different countries may vary, and therefore having more specific data might help.
Okay. There are several data sets on the internet of tick images or image data set, but we don't have the thermographic imaging yet that is accessible to everyone. Hence, I had to go and capture the images and also try to see if it works. Currently, there's no any data set on thermal images, but it is there on the normal images. So since I was, my algorithm is based on using the thermographic imaging technology, I had to go out and take the pictures myself, and then edit the images, crop out everything, and then do train the algorithm on that.
No, but I think that to me is a feature, not a bug, because that helps you build your experience. And that means that you be more sensitive to images you're getting from other people because you know what's involved and you know what you need and what you need to look for. Does anybody else have any questions or comments for this presentation? In which case, Fhulufhelo, thank you very much indeed for a very interesting presentation. And this brings us to the end of the eAgriculture track and indeed the end of this year's conference, which is very sad. So we look forward to seeing as many of you as possible in Swanee next year. And we look forward to a strong response to the call for papers, which as Miriam says, will open in the coming month or so. So, and I hope you all have a very good weekend.